Above us, on clear nights, the sky can appear calm and still. But for most of human history, the night sky was not thought of as empty space. It was understood as a place filled with order, a place of lights that moved in patterns. People watched those patterns for seasons, for navigation, and for meaning. They noticed that some stars seemed fixed. Others wandered. Those wandering lights became planets. Yet even in these early observations, there was a quiet question. Could there be things in the heavens that could not be seen at all? The idea sounds modern, but in a simple form it is very old. Ancient cultures often imagined hidden regions beyond visible stars. Not black holes in a scientific sense, but unseen domains, places where ordinary understanding ended. Much later, during the scientific revolution, questions about invisible objects took a more mathematical form. In the 17th century, Isaac Newton described gravity as a universal force. The same force that made an apple fall could hold the moon in orbit. This was a profound change. It meant the heavens followed the same rules as Earth. And once gravity was understood as universal, people could begin asking unusual questions. If gravity pulls matter together, could enough matter pull so strongly that even light could not escape? In 1783, an English natural philosopher named John Michell proposed something remarkable. He imagined what he called a dark star, a star so massive and so compact that its escape velocity would exceed the speed of light. Escape velocity is a simple idea. It is the speed needed to leave a gravitational field without falling back. For Earth, rockets must reach this speed to escape into deep space. Michel asked what would happen if a star's escape velocity became greater than light itself. Under the physics known at the time, light was often thought of as made of particles. If those particles were affected by gravity, perhaps they could be trapped. It was not modern black hole theory, but the seed of the idea was there. Around the same time, Pierre-Simon Laplace proposed something similar. Again the notion appeared. A body so dense it would be invisible. This is striking because these ideas emerged long before relativity, long before telescopes could detect galaxies, long before anyone imagined collapsed stars. The concept began not with observation, but with reasoning. Yet the dark star idea faded. In the 19th century, wave theories of light became dominant. If light was a wave rather than particles, Michel's reasoning seemed less convincing. Interest drifted away. For a time, invisible stars slipped into the background of science. But gravity remained mysterious. Newton's theory could describe attraction precisely. It could predict orbits beautifully. Yet it did not explain what gravity truly was. It acted across empty space. Instantly, it seemed. Even Newton found that unsettling. This unanswered question lingered for centuries. Then, in the early 20th century, Albert Einstein transformed the problem entirely. Gravity, in his view, was not a force pulling objects together in the old sense. Gravity was geometry. Matter bends space-time. Curved space-time guides motion. Planets orbit not because they are tugged by invisible strings. They follow paths through curved space-time. This was the beginning of general relativity, published in 1915. And almost immediately, strange implications appeared. Einstein's equations allowed extreme objects where space-time might curve without limit. In 1916, Carl Schwarzschild found a solution to Einstein's equations. He was serving on the front during the First World War when he derived it. His solution described the space-time around a spherical mass. And hidden within the equations was something astonishing. A boundary appeared, a radius beyond which escape would be impossible. Today, this is called the Schwarzschild radius. For a mass compressed inside this radius, an event horizon would exist. That term came later, but the mathematics was already there. Curiously, even Einstein doubted such objects would exist in nature. Many physicists did. They often treated these solutions as mathematical oddities. The idea of a real collapsed object seemed too strange. This is a recurring pattern in science. Equations sometimes reveal possibilities before nature confirms them. For decades, black holes existed mostly as possibility, a puzzle in equations. The phrase black hole itself did not become common until the 1960s. It is often associated with John Wheeler. Before that, descriptions were more awkward. Gravitationally completely collapsed objects, frozen stars. The simpler name endured. But to understand why the idea was so difficult to accept, it helps to pause on what it implies. A black hole is not merely a dark object. It is not a cosmic vacuum cleaner pulling everything inward. That is a common misconception. If our sun were replaced by a black hole of equal mass, Earth would continue orbiting much the same way. Gravity at distance would remain similar. The strangeness lies not in distant pull, but in what happens near the boundary. And that boundary emerged first through thought, through mathematics, through careful logic. There is something gentle in that history. Before black holes were observed, they were imagined. Before they were photographed indirectly, they were derived on paper. Human understanding often begins this way, quietly, with a question that sounds impossible. As astronomy advanced, evidence began accumulating for extreme compact objects. In the 20th century, scientists studied white dwarfs, dense stellar remnants supported by quantum pressure. Then, neutron stars were predicted, even denser remnants. Matter compressed to astonishing extremes. This raised a new question. If gravity could overcome the forces supporting white dwarfs, and even neutron stars could collapse continue further. In the 1930s, Subramanian Chandrasekhar studied mass limits for white dwarfs. Above a certain mass, such stars cannot remain stable. Later, work by Oppenheimer and others explored gravitational collapse more deeply. They showed that under some conditions, collapse may continue relentlessly. Here, black holes began shifting from abstraction toward astrophysical possibility. Still, even then, the concept resisted intuition. Human thought evolved in ordinary environments. We do not naturally picture curved space-time or trapped light. So physicists often used analogies. A well in a landscape, a river flowing toward a waterfall, a surface bending beneath weight. These analogies are incomplete. Yet they help the mind approach unfamiliar structure. And perhaps that is part of the mystery of black holes. They sit at the edge of intuition. We can describe them mathematically with precision, yet ordinary imagination strains to picture them. There is another subtle reason the black hole idea is fascinating. It arose through a reversal of expectation. For much of history, stars symbolized light, warmth, illumination. Yet here was a possibility in which a star's final fate could become darkness. Not empty darkness, but a region defined by gravity itself. This transformed cosmic imagination. And still, even with theory developing, evidence remained indirect for decades. Astronomers could infer unseen massive companions through orbital motion. They could observe energetic X-ray sources from matter falling inward. But a black hole itself emits no direct light. One studies its influence. In this way, black holes resemble some other deep scientific entities. We often know them by effects, by what they do, not by seeing them plainly. This can make them feel mysterious. Yet there is nothing supernatural in that mystery, only the ordinary mystery of nature exceeding intuition. It is worth remembering that black holes were not invented as exotic speculation. They emerged because existing theories pointed toward them. Newton opened the first conceptual door. Michel and Laplace imagined dark stars. Einstein changed gravity into geometry. Schwarzschild revealed hidden structure in the equations. Stellar physics made collapse plausible. Piece by piece, an impossible object became a scientific subject. There is a quiet lesson in that progression. Great mysteries often arrive gradually, not as sudden revelations, but as layers of understanding settling into place. And black holes remain mysterious partly because they unite many layers at once. Gravity, light, matter, time. They sit where familiar concepts begin to blur. But before reaching event horizons or singularities, there is something simpler to understand. The very idea that gravity can shape the stage on which reality unfolds. Because without that idea, black holes remain only strange dark objects. With that idea, they become consequences of space-time itself. And this shift from force to geometry is where the deeper story truly begins. So now we can move gently toward how gravity bends space itself, and how that bending makes black holes possible. Gravity can feel familiar because we live inside it constantly. We walk under its influence. We feel its pull without thinking about it. Things fall. Planets orbit. For much of history, this seemed simple. Objects attracted one another. That was Newton's great description. And it worked extraordinarily well. It explained falling apples and lunar motion with the same mathematics. It predicted planetary orbits with stunning precision. Yet there was a quiet problem hidden inside that success. Newton described what gravity does, but not what gravity is. How could one object influence another across empty space? What carried that influence? Even Newton was uneasy about that question. Centuries later, Einstein offered a radically different answer. Gravity, he proposed, is not a force in the ordinary sense. It is the shape of space-time. This idea can seem abstract at first, so it helps to move slowly. Space is often imagined as emptiness, a passive stage where events happen. Time is often imagined as separate, a steady flow moving forward. Einstein joined them together. Space and time became one structure, space-time. And according to general relativity, mass and energy affect its geometry. Matter tells space-time how to curve. Curved space-time tells matter how to move. That sentence is often repeated because it captures the heart of the theory. Matter tells space-time how to curve. Curved space-time tells matter how to move. It is simple to say, but profound to absorb. Imagine rolling a marble across a flat floor. It travels in a straight line. Now imagine the floor subtly bent. The marble's path curves, not because something pulls it sideways, but because the surface itself guides its motion. This analogy is imperfect. It uses gravity to explain gravity, which has limitations. But it hints at the idea. Earth orbits the sun not because an invisible rope pulls it around. Earth follows a natural path through curved space-time around the sunday. In relativity, this natural path is called a geodesic, the closest thing in curved space-time to a straight line. Even falling changes meaning. In Newton's picture, a falling object is pulled downward by force. In Einstein's picture, a falling object follows the geometry of space-time. This sounds strange, yet experiments confirm it again and again. Light bends around massive objects. Time runs more slowly in stronger gravity. Clocks on satellites tick differently than clocks on Earth. Even global positioning systems must account for relativity to function accurately. So this is not poetic language. It is measurable structure. Once gravity becomes geometry, something new becomes possible. Space can curve gently, or extremely. And if enough mass occupies a small enough region, curvature can become so severe that escape becomes impossible. Here, the road toward black holes begins to appear. But first, there is a simpler concept to linger with: escape velocity. If you throw a stone upward, it falls back. Throw it faster, it rises higher. Fast enough in principle, it escapes Earth entirely. That threshold is escape velocity, about 11 kilometers per second for Earth. Larger masses have higher escape velocities. More compact masses do too. Compress enough mass into enough smaller region, and escape velocity can exceed the speed of light. In Newtonian language, this echoes Michel's dark stars. In relativity, the deeper explanation becomes the event horizon. An event horizon is often misunderstood. It is not a solid shell, not a wall, not a surface you collide with. It is a boundary in space-time, a one-way boundary. Outside it, paths may lead outward. Inside it, all possible future-directed paths lead inward. Even light follows those paths. That is why light cannot escape. It is not that gravity reaches out and drags photons backward. It is that space-time itself is shaped so all routes forward lead deeper in. This is subtle, but it matters. Black holes are not traps imposed on space-time. They are structures of space-time. Sometimes physicists use a river analogy. Imagine swimming in calm water. You can move upstream or downstream. Now imagine drifting toward a waterfall where the current strengthens. At some point, the river flows faster than you can swim. Beyond that point, all motion carries you over. The analogy is incomplete, but it gestures toward an event horizon. Another strange implication follows. Gravity affects time itself. This is gravitational time dilation. Clocks deeper in gravity run slower relative to distant clocks. Near a black hole, this effect becomes extreme. Imagine a traveler falling toward an event horizon while a distant observer watches. The distant observer sees the traveler appear to slow. Signals stretch to redder wavelengths. The traveler seems to fade near the horizon. Yet the traveler, in their own experience, crosses onward in finite time. This often feels paradoxical, but it reflects how relativity ties observation to reference frame. Different observers describe events differently, yet consistently. Here, black holes begin revealing something deeper. They are not merely objects among objects. They expose the structure of reality. Even ordinary orbiting becomes richer through this lens. Mercury's orbit, for example, shifts slightly in a way Newtonian gravity could not fully explain. General relativity accounted for it. Light from distant galaxies bends around foreground galaxies. This is gravitational lensing. Space acting almost like optics. Entire galaxies can become cosmic lenses. Their mass warps light into arcs and rings. These are not exotic exceptions. They are consequences of the same geometry that permits black holes. The theory holds together as one fabric. There is also an important distinction between strong and weak gravity. Around Earth, space-time curvature is gentle. Around the Sun, stronger. Near a neutron star, stronger still. Black holes represent an extreme limit, a region where curvature becomes dominant in ways ordinary intuition scarcely handles. Yet black holes are not the only lesson here. The broader lesson is that geometry can govern physics. That is extraordinary. The shape of space-time determines motion. Time itself participates. In daily life, space feels passive and time feels universal. Relativity quietly overturns both impressions. This is one reason black holes fascinate physicists. They push these truths into dramatic clarity. Near a black hole, ordinary categories begin bending. Distance behaves strangely. Time behaves strangely. Causality acquires boundaries. Yet all this grows from one calm premise. Space-time has geometry. Sometimes it helps to think historically again. Before Einstein, no one suspected gravity could slow clocks, or bend starlight, or create horizons in space-time. These were hidden in nature all along, waiting for the right language. And once that language existed, black holes ceased being fantasy. They became consequences. This matters philosophically too. A black hole is not an arbitrary cosmic monster. It is what gravity naturally permits when pushed far enough. There is elegance in that. It is also worth correcting another misconception. People sometimes imagine black holes as endlessly sucking nearby stars inward. But gravity outside a black hole behaves according to its mass, spin, and charge, just as relativity describes. A black hole does not reach farther simply because it is a black hole. Its mystery lies in the horizon and interior, not in magical pulling power. Precision matters here. Mystery grows clearer, not dimmer, when misconceptions fade. Another gentle way to picture curvature is through straight paths on curved surfaces. On a globe, lines of longitude seem parallel at the equator, but meet at the poles. Geometry itself changes expectation. In curved spacetime, motion can likewise seem surprising while remaining natural within the geometry. This is why physicists often say gravity is not really a force in general relativity, though in many practical cases, treating it as force works well. Both descriptions can coexist at different levels. But for black holes, geometry becomes essential. It also prepares us for an even stranger thought. If space-time can curve enough to create horizons, what happens when matter itself collapses to create such curvature? Where do black holes come from physically? How does nature make them? To answer that, we turn not to geometry alone, but to stars. Because black holes are not only equations. Many are born from stellar death. Massive stars spend millions of years balancing two tendencies. Gravity pulls inward. Pressure from nuclear fusion pushes outward. A long equilibrium holds. A quiet tension. But when fusion can no longer support the star, gravity may win. And when gravity wins completely, space-time itself may fold into something extraordinary. That story carries us from the geometry of black holes to their birth, from curved space-time to collapsing suns. And perhaps there is something fitting in that movement. We began by asking how gravity bends reality. We arrive at the possibility that dying stars can bend it beyond return. So now we can drift gently toward how stars end and how some of those endings become black holes. A star can shine for millions or billions of years, quietly converting mass into energy, holding itself in balance. That balance is delicate, though often long-lasting. Gravity pulls inward. Pressure pushes outward. As long as those forces remain in equilibrium, a star endures. Much of a star's life is this long negotiation. Inward pull, outward resistance. A cosmic balance held through nuclear fusion. In the core, hydrogen nuclei fuse into helium. Energy is released. Heat and radiation support the star against collapse. This state is called hydrostatic equilibrium, a calm phrase for something profound. A star exists because gravity and pressure remain in tension. But equilibrium depends on fuel, and fuel is finite. Eventually, changes begin. In stars like our Sun, the ending is gentle by cosmic standards. Outer layers expand. a red giant phase emerges. Later, the outer layers drift away. The core remains as a white dwarf. Dense, hot, but no black hole forms. For black holes, we need something more massive. Very massive stars live differently and die differently. Their cores progress through heavier fusion stages. Hydrogen to helium, helium to carbon, then onward in some cases through oxygen, neon, silicon. Each stage shorter than the last. The final stages can be astonishingly brief. And then comes iron. Iron changes the story. Fusion of iron does not release net energy the way lighter element fusion does. It costs energy. The engine falters. Pressure support weakens. Gravity begins to win. What follows can happen with extraordinary speed. The core collapses inward. Matter falls. Densities soar. Electrons and protons can combine into neutrons. A neutron-rich core forms. Sometimes collapse halts there. A neutron star remains. But if the remnant mass is large enough, even neutron degeneracy pressure may not hold. Collapse continues toward black hole formation. This threshold depends on details. Rotation matters. Composition matters. Mass loss matters. Nature is rarely a single simple number, but the broad picture stands. Some massive stars end in collapse so complete that an event horizon forms. Often this is associated with a supernova, though not always in the dramatic textbook way. In many core collapse supernovae, outer layers are blasted into space. Heavy elements are dispersed. Ironically, some atoms in our bodies were forged through such stellar endings. Collapse and creation intertwined. There is a quiet beauty in that. Death of a star, helping seed future worlds. Yet inside the remnant region, gravity may continue beyond recovery. This is where general relativity becomes essential. Newtonian gravity can suggest collapse. Einstein's theory reveals what complete collapse can mean. Space-time geometry itself bends toward horizon formation. It is worth pausing on what is not happening. A black hole is not a hole torn in material fabric, not a tunnel punched into emptiness. It is a region where gravity has shaped space-time so strongly that escape beyond a boundary becomes impossible. That boundary, the event horizon, will soon deserve its own attention. But first, the collapse itself. It can feel almost paradoxical that immense stars, symbols of radiant stability, can end in darkness. But the same gravity that helped form them never disappeared. It was only balanced. When support fades, gravity resumes its patient work. Sometimes people imagine black holes as cosmic vacuum cleaners suddenly sucking everything nearby inward. But formation does not create magical new suction. If our sun were somehow replaced by a black hole of equal mass, Earth's orbit would in principle remain similar. There would be darkness, but not immediate swallowing. Gravity depends on mass and distance, not on whether the mass is a star or black hole at the same total mass. Misconceptions often hide elegant truths. There are also pathways beyond single-star collapse. Black holes can grow by mergers. Two black holes orbit. Gravitational waves carry away energy. They spiral together. A larger black hole forms. Some stellar mass black holes may have grown partly through repeated mergers. And much larger black holes may arise through long histories of accretion and merging. Those supermassive giants we will return to later. For now, stay with stellar death. It is striking how black holes emerge not from exotic substances introduced from elsewhere, but from familiar matter pushed into extraordinary conditions. Hydrogen, helium, the same ordinary ingredients. Extremes reveal unfamiliar behavior. This is a recurring theme in physics. Ordinary laws, extraordinary regimes. Another subtle point often matters. Black holes are not only predicted by equations in abstraction. Stellar evolution theory naturally points toward them. They arise not as decorative possibilities, but as consequences of known processes. This helped shift black holes from speculation into accepted astrophysics. Theory and stellar observation reinforced one another. Some stars must leave dense remnants. Some remnants exceed neutron support. Collapse continues. The logic has a severe elegance. There is also the question of singularity. Classical general relativity suggests collapse may continue toward a singularity, a region where known equations signal breakdown. Infinite density appears in the classical picture. Many physicists suspect a future theory of quantum gravity may alter that description. But outside the horizon, much of black hole physics does not depend on resolving the singularity. That, too, is worth remembering. One can understand horizons and external effects without fully knowing the ultimate interior fate. Science often progresses this way. Partial understanding before complete theory. There is another emotional layer to stellar collapse that often goes unnoticed. Black holes sound abrupt, but they are the end of long stellar biographies. Millions of years of quiet burning may precede seconds of collapse. Vast patience ending in sudden transition. Nature often works on such mixed tempos. Slow preparation. Rapid change. In some cases, collapse may even produce gamma-ray bursts associated with extreme jets. These belong to specialized scenarios, often involving rotation and particular structures. We need not dwell there, but they remind us collapse can be diverse. There is not one single dramatic script repeated identically. And still, beneath variations, the central story remains gentle in logic. Gravity presses inward. Pressure resists. Fuel ends. Resistance fails. Collapse proceeds. Sometimes a black hole forms. Repetition can clarify. The mystery often becomes calmer when reduced to structure. One can almost hear in this story an echo of the earlier escape velocity idea. If gravity grows strong enough, escape fails. Here, collapse builds the object where that becomes literal beyond a horizon. Earlier, black holes were conceptual possibilities. Now they emerge from dying stars. The mystery grows more physical. Yet once a black hole forms, a deeper question arrives. What exactly marks the boundary between outside and no return? What is the event horizon really? Is it a surface? A wall? A place one would feel? These questions have fascinated scientists and storytellers alike. And they lead from collapse into one of the most subtle ideas in modern physics. A boundary defined not by material, but by causality itself. So now we can move gently toward the event horizon and the strange threshold where escape ceases to be possible. Imagine approaching a boundary that is not a wall, not a surface of stone or metal, not something visible hanging in space. Yet it marks a profound division, a threshold in reality itself. This is the event horizon. The phrase can sound dramatic, but its meaning is precise. It is the boundary beyond which events can no longer influence distant observers. Light emitted inside cannot reach outward. Signals cannot return. Causal contact is cut off. That is why it is called a horizon. Like a horizon at sea, it marks a limit to what can be seen beyond. But unlike an ordinary horizon, this one is woven into space-time. It is important to move slowly here. Many popular images make the event horizon seem like a glowing ring or spinning edge. Those images often depict matter outside the horizon, in hot accretion disks. The horizon itself is not a luminous border. It has no material texture. You do not strike it like a surface. For a sufficiently large black hole, a traveler crossing it might notice nothing special at that exact moment. That surprises many people. We imagine crossing such a boundary should feel dramatic. But physics suggests otherwise. Locally, if tidal forces are weak enough, the crossing may be uneventful. The significance lies not in a local jolt, but in the structure of future possibilities after crossing. That is a subtle idea. So it helps to return to something familiar. In ordinary life, you can move through space in many directions. Forward, backward, left or right. In space-time, we also move through time, always forward. Near a black hole, space-time curvature becomes so extreme that inside the event horizon, moving inward becomes as inevitable as moving toward tomorrow. That is one reason physicists sometimes say the singularity lies in your future once you cross, not in the sense of a place you might choose to avoid, but as a direction built into space-time. This is what makes the horizon strange. It is not a prison door closing behind you. It is a change in what future paths exist. Another way to approach this is through escape. Outside the horizon, light can still move outward. Paths exist that lead away. At the horizon, outward light rays hover at the threshold. Inside, even outward-directed light ends up moving deeper inward. That is why escape fails. Not because engines lose power, not because some force grabs hold, but because geometry allows no outward route. This idea can feel abstract. So physicists sometimes return to the river analogy. Imagine floating toward a waterfall. Far upstream, you can paddle away. Closer in, the current strengthens. At a certain line, the river flows faster than any swimmer can move against it. Cross that line, and all paths carry downstream. Again, no analogy is perfect, but it suggests inevitability without requiring a physical wall. There is another mystery at the horizon. It depends on who is observing. Suppose a traveler falls toward a black hole while a distant observer watches from far away. From the traveler's perspective, time feels ordinary. They fall onward. Their wristwatch ticks normally. But to the distant observer, something remarkable happens. The traveler appears to slow as they approach the horizon. Their signals become stretched. Their light redshifts. In principle, they seem to freeze near the edge. This has led to many misunderstandings. Some conclude the traveler never crosses. But that is not quite right. It reflects how coordinates and observation behave in relativity. Different descriptions arise from different frames. Neither cancels the other. The traveler crosses in finite, proper time. The distant observer never receives signals confirming passage. Both statements coexist. This is one of the first places black holes challenge everyday intuition about time. Time is not behaving as a universal backdrop. It is participating in the geometry. And because this is a sleep journey, it is worth lingering with that gently. Time participates. Time bends. Time stretches. Black holes make this impossible to ignore. People often ask what one would see while falling in. The answer depends strongly on the black hole's size. For a stellar mass black hole, tidal forces near the horizon may already be severe. Gravity at your feet could differ enormously from gravity at your head. These differential forces can stretch objects. This is sometimes called spaghettification. The term is playful. The physics is serious. Yet for a supermassive black hole, the horizon may be crossed before tidal forces become extreme. In that case, the boundary itself could be crossed with little immediate local drama. That distinction matters. The horizon and destructive tidal forces are not identical ideas. They can occur in different regions. Another question arises quietly. Does the event horizon have temperature? Surprisingly, modern physics suggests yes, in a subtle sense. Through quantum effects linked to Hawking radiation, black holes can be assigned temperature and entropy. That mystery belongs later. But it hints the horizon is not merely a geometric boundary. It may also hold deep thermodynamic meaning. Even here, the mystery thickens gently. There is also the famous question of what happens at the horizon according to an infalling traveler. Classical general relativity says, for large black holes, nothing singular need happen there locally. But modern debates, such as discussions of hypothetical firewalls, ask whether quantum effects might complicate this picture. These remain unresolved questions. For now, the classical picture remains our guide. Crossing the horizon need not feel like crossing a physical membrane. There is a quiet elegance in that. The most important boundary in black hole physics may be invisible to the senses, defined not by substance, but by causality. That word is worth pausing over. Causality. It means the structure of cause and effect. What can influence what? Black holes are extraordinary, partly because they reshape causal structure. They redraw what can communicate with the wider universe. That is deeper than darkness. It is a rearrangement of possible influence. Sometimes people ask whether crossing the horizon means falling into a point instantly. No, not instantly. After crossing, there remains an interior journey. For a non-rotating black hole, that journey ends at the singularity in finite proper time. For rotating black holes, the interior may be even stranger in theory. Those mysteries wait ahead. But even before going inward, the horizon itself has reshaped modern physics. It forced scientists to ask whether information is truly lost. It inspired thermodynamic analogies. It touched quantum theory. A boundary once thought a mathematical oddity became central to fundamental physics. There is also beauty in its simplicity. For a non-rotating black hole, the horizon radius depends mainly on mass. More mass means a larger horizon. That means supermassive black holes can have horizons larger than planetary orbits. Vast regions defined by no visible surface. It is difficult to picture, and perhaps that is part of the wonder. We often trust only what resembles familiar objects. Yet the universe is under no obligation to conform to ordinary intuition. Black holes remind us of that quietly. Another subtle point matters. The event horizon is different from the apparent glowing ring seen in black hole images. The bright structures arise from hot matter outside. The dark shadow relates to light paths near the black hole, not a direct view of the horizon as an object. Precision here deepens appreciation. Much of black hole mystery lies in not confusing visualization with literal structure. If all this feels conceptually demanding, that is natural. Horizons challenge ordinary categories, but the logic beneath them is calm. There exists a boundary. Beyond it, outward futures vanish. Crossing it may feel locally ordinary, yet globally everything changes. That is the essence. And notice something beautiful. We began long ago with Michel imagining light unable to escape a dark star. Here, that old intuition has become richer. Not merely light trapped by strong pull, but space-time arranged so escape loses meaning. The mystery has deepened, but also clarified. Sometimes science does that. It replaces a simple, strange idea with a stranger but more coherent one. Yet for all the fascination of the horizon, it is still only the edge, a threshold, a beginning. Because once crossed, deeper questions emerge. What lies inside? Does space-time continue smoothly? Does it end in singularity? What of rotating black holes, wormhole speculation, and the limits of theory? Those questions lead beyond the horizon into geometry even stranger, into places where our equations begin to strain. And so the horizon, far from concluding the mystery, serves as its doorway, a silent threshold between what can return and what cannot. So now we can drift inward, toward the strange geometry thought to exist inside black holes. The event horizon is often imagined as a kind of surface, a dark shell. a boundary one might collide with. But in general relativity, it is stranger and quieter than that. The event horizon is not a material wall. It is not made of substance. It is a boundary in space-time, a limit beyond which events cannot send signals outward to distant observers. It is defined by causality. That word matters. Causality concerns what can influence what. Outside the horizon, light can still, in principle, move outward. Inside, all future directed paths lead deeper inward. Even light cannot escape. This already stretches ordinary thought. We are used to space as a place where directions are choices. Near and within a black hole, geometry changes what future paths exist. To understand why time becomes central here, it helps to recall something from relativity more broadly. Time is not universal in Einstein's physics. It can flow differently for different observers. Motion affects it. Gravity affects it. This is called time dilation. Even on Earth, clocks at different gravitational potentials tick at slightly different rates. This is not abstraction. It is measured reality. Satellite systems such as Global Positioning System account for relativistic timing corrections. So, when black holes intensify these effects, we are extending known physics into stronger gravity. Now imagine an observer far from a black hole watching someone fall inward. What appears? In the distant observer's description, the falling person seems to slow as they approach the horizon. Signals arriving from them become increasingly redshifted. Light stretches toward longer wavelengths, fainter, redder. Their clock appears to run slower. In a limiting sense, they seem to freeze near the horizon. This image has entered popular imagination. Someone suspended forever at the edge. But this is only part of the story. It is how the distant observer describes events. For the person falling, something different happens. In their own proper time, they cross the horizon in finite time. They do not encounter a cosmic stop sign. For a sufficiently large black hole, crossing might not locally feel dramatic at the horizon itself. No wall, no flash. Just passage across a causal boundary. This seems contradictory at first. Frozen from one perspective, crossed from another. But relativity often carries such dual descriptions. Neither is false. They reflect different observers. This is one of those places where intuition must soften. It is tempting to ask, which view is the real one? Relativity resists that framing. Physical description depends on frame. That is part of the lesson. There is a beautiful mathematical way to glimpse why horizons confuse intuition. In some coordinate systems, the horizon looks singular. Equations appear to break. But other coordinates remove that apparent singularity. Revealing it was partly a coordinate artifact. The horizon is subtle, but not in itself necessarily a place of infinite physical drama. The singularity question lies deeper inside. Time dilation near black holes often leads naturally to thought experiments. Suppose one astronaut hovers far away while another approaches the horizon and returns, if possible, from outside the horizon. Their clocks can disagree. different elapsed times. This is no fantasy invention. It follows from relativity's structure. Near extreme gravity, time itself behaves relationally. That phrase alone can quiet the mind. Time behaves relationally. It reminds us time is richer than everyday habit suggests. There is also gravitational redshift. Light climbing out from strong gravity loses energy in frequency. Near a black hole, this effect intensifies enormously. Signals stretch. Information outward becomes harder to transmit. Again, time and light intertwine. Another famous idea enters here: spaghettification. The name sounds playful. The physics is tidal forces. Gravity can differ across an extended object. If your feet feel much stronger pull than your head, stretching occurs. For small black holes, these tidal forces near the horizon can be immense. For supermassive black holes, they may be far gentler at the horizon. This surprises many people. Bigger black hole can mean gentler local horizon crossing. Again, intuition bends. But our focus here is time. And black holes make time feel almost topological. Outside the horizon, moving away from the center remains part of possible futures. Inside, in a sense often described carefully, moving toward the singularity can become as inevitable as moving toward tomorrow. That comparison is imperfect but evocative. It hints why, inside horizons, ordinary spatial intuition fails. Some popular stories say time stops at a black hole. Better to be precise. Time does not simply stop. Different observers assign different temporal descriptions, and extreme dilation appears. Precision makes the wonder deeper, not less. There is also a psychological reason these ideas fascinate. Time feels intimate. We live inside its passage. So, when physics says time can stretch under gravity, the universe feels suddenly stranger in a personal way. Yet these are not fantasy loopholes for ordinary time travel in simplistic terms. Black holes do not offer easy science fiction shortcuts. They offer something subtler. They reveal time was never quite what common sense assumed. There is a recurring calm in this realization. Mystery grows, but through logic. Another point deserves care. The freezing at the horizon seen by distant observers is connected to signals received. Practical observations involve fading and redshift. One does not literally watch an eternally crisp, frozen figure. Light dwindles. The popular image oversimplifies. Often, oversimplifications are seeds, worth refining, not discarding. There are even deeper geometries, such as rotating black holes, described by the Kerr metric. Rotation introduces richer structures, frame dragging, ergospheres. Space itself can be dragged by spinning mass. Astonishing, but predicted and related effects are observed in weaker regimes around rotating bodies. We need not go far into that here. It is enough to sense black holes are even richer than non-rotating pictures suggest. There is almost a pattern now. Escape velocity led us toward black holes. Collapse gave them birth. Horizons defined boundaries. And time itself bends around them. Each layer grows stranger, yet each follows from extending known principles. That continuity matters. Black holes are not violations of physics. They are extreme expressions of it. There is quiet comfort in that. One can imagine standing far from a black hole, watching clocks disagree, light redden, futures diverge. Not chaos, but geometry unfolding. This is perhaps the deeper beauty of relativity. It turns what feels metaphysical into structure. And still, black holes widen further. Thus far, we have spoken mostly of stellar black holes and horizons. But there exist black holes so immense they sit at the centers of galaxies and may help shape them. Giants far beyond stellar remnants. To move from time bending near a horizon to black holes steering galactic history is a remarkable widening of scale. So now we can move gently towards supermassive black holes and the hidden engines at the hearts of galaxies. A black hole can begin as the collapsed remnant of a star. That alone is astonishing. But some black holes are vastly larger than anything a single star could produce. Not 10 times the sun's mass. Not 100. But millions or even billions of solar masses. These are supermassive black holes. They sit, as far as observations suggest, at the centers of most large galaxies, including our own. This realization transformed how astronomers think about galaxies. Once, galaxies were often imagined mainly as vast collections of stars, gas, and dark matter. Now we understand many have extraordinary gravitational engines at their cores. Quiet sometimes, violently active at other times. And these central black holes may help shape the history of galaxies themselves. Our own galaxy, the Sagittarius A times black hole, has a mass of roughly 4 million suns. It lies near the center of the Milky Way, about 26,000 light-years away. We do not see the black hole directly. We infer it from the motion of stars orbiting something compact and enormously massive. For decades, astronomers tracked those stellar orbits. Some stars sweep around the invisible center in remarkably tight paths. Their speeds reveal the mass hidden there. This was among the strongest evidence that supermassive black holes are real astrophysical objects. And yet Sagittarius A times is modest compared with some giants known elsewhere. At the center of the galaxy, Messier 87 lies a black hole with billions of solar masses. This was the first black hole whose shadow was imaged by the Event Horizon Telescope collaboration. But long before imaging, quasars had already hinted at such monsters. Quasars were among the strangest discoveries in 20th century astronomy. They looked star-like in telescopes, yet their spectra revealed enormous distances, which meant they were unimaginably luminous, some outshining entire galaxies. At first, this seemed nearly impossible. What could power something so bright? Nuclear fusion alone struggled to explain it. The answer emerged gradually. Matter falling toward a supermassive black hole can release tremendous energy. Not because the black hole emits light itself, but because infalling matter forms an accretion disk. Gas spirals inward. Friction and magnetic effects heat it enormously. It can glow across the electromagnetic spectrum, radio waves, visible light, X-rays. In active galactic nuclei, these processes can generate jets stretching thousands of light years. Great beams of particles launched from near the black hole's vicinity, often guided by magnetic fields linked to the spinning system. The scale is difficult to picture. Entire galactic cores lit by matter falling toward darkness. There is a paradoxical beauty there. Some of the brightest objects in the universe are powered by regions associated with blackness. Yet supermassive black holes are not merely spectacular engines. They may participate in shaping galaxies themselves. This idea is often called black hole feedback. The concept is subtle. If a central black hole feeds actively, radiation and jets can affect surrounding gas, heating it, pushing some of it outward. That may regulate star formation. Too much gas cooling could form stars rapidly. Feedback can alter that process. In this view, galaxy and black hole may evolve together. Remarkably, the mass of a galaxy's central black hole often correlates with properties of the galactic bulge. This suggests some deep connection. Cause and effect remain active research topics, but the link appears meaningful. Once, black holes seemed like isolated endpoints. Now they may be participants in cosmic structure. There is something almost quieting in that shift. Objects once imagined as devourers may also help organize. Another mystery follows naturally. How did supermassive black holes grow so enormous? This remains partly unresolved. Several pathways are studied. Perhaps small black holes from early stars grew through accretion and mergers over cosmic time. Or perhaps some massive seeds formed more directly from collapsing primordial gas clouds. Some observations suggest very massive black holes existed surprisingly early in cosmic history. That makes growth timescales an ongoing puzzle. Even here, mystery persists. Black holes often do. There is also the question of galactic mergers. Galaxies collide and merge over billions of years. If each hosts a central black hole, those black holes may eventually spiral together. Their dance may emit gravitational waves. Their merger may build larger black holes. So the giants may grow partly by cosmic union. Sometimes people picture a supermassive black hole at a galactic center swallowing nearby stars constantly. Reality is usually calmer. Most stars in a galaxy orbit safely at enormous distances. The central black hole influences the galactic core, but does not act like a universal drain. Misconceptions often exaggerate. Precision reveals something more elegant. Consider our own sun orbiting the Milky Way's center. It completes one galactic orbit in roughly 200 million years. We move within a galaxy whose center contains a supermassive black hole. Yet life proceeds under quiet skies. That perspective is calming. These giants exist. Yet the cosmos is mostly spacious. Supermassive black holes also stretch imagination in scale. A stellar black hole may span tens of kilometers. A supermassive horizon may exceed planetary orbits. For the largest known examples, the event horizon can rival the size of our solar system. Vast boundaries of no material surface. Purely geometric thresholds. It remains astonishing that general relativity permits such structures. There is another quiet wonder. Because supermassive black holes are so large, tidal forces at their horizons may be comparatively gentle. In principle, crossing such a horizon could be locally uneventful. That idea can feel counterintuitive. Larger black hole, gentler local crossing. Yet geometry allows it. These giants repeatedly overturn intuition. And then there are the jets. It is worth lingering on them. Some active supermassive black holes launch narrow streams moving near light speed. These can extend far beyond their host galaxies. The mechanisms involve accretion, magnetic fields, and often black hole spin. There are still open questions. But they reveal that black holes are not simply endpoints of collapse. They can sit at the center of astonishing dynamical systems. Darkness, surrounded by extraordinary activity. Some researchers even ask whether black holes played a role in early galaxy assembly itself. Did galaxies build around black holes? Or did black holes grow inside, forming galaxies? The relationship may be intertwined, co-evolution rather than one-way causation. Again, the theme returns. Black holes resist simple roles. They are not only destroyers, not only relics, but actors in cosmic architecture. This broadens the mystery beautifully. Earlier, black holes appeared as extreme consequences of stellar death, then as strange geometries beyond horizons. Now they stand woven into galaxies themselves. The scale keeps widening. There is also something humbling in the fact that our Milky Way quietly carries such a giant at its center. For most human history, no one knew. Yet it was always there. Another reminder that discovery often reveals hidden structures rather than inventing them. And still, even supermassive black holes were long inferred rather than directly imaged. Their presence emerged through orbits, radiation, and theory. Until recently. The imaging of black hole shadows changed something cultural as well as scientific. It gave form, however indirect, to what had long been abstract. Yet even before imaging, the evidence was already compelling. Science often becomes certain before it becomes picturable. That is worth remembering. There is one more gentle mystery. Some have wondered whether black holes might help explain dark matter. Ordinary supermassive black holes cannot account for dark matter overall. But primordial black hole hypotheses remain explored in some contexts. Those questions belong later. For now, the central lesson is already rich. Black holes may help govern galaxies, feed quasars, launch jets, regulate star formation. They are woven into cosmic history. And perhaps that changes how we hear the phrase black hole. It no longer suggests only isolated darkness. It suggests hidden engines at the hearts of galaxies. Quiet sometimes, luminous sometimes, ancient always. Yet for all we infer, another question naturally follows. How do we actually observe these invisible things with confidence? How did we move from indirect inference to something like seeing. How did we listen to space-time ring when black holes collide? Those questions lead from cosmic giants to the remarkable ways humans have detected black holes themselves. So now we can move gently toward the black holes we have actually seen and how invisible objects became observable. For a long time, black holes lived mainly in mathematics, inference, and careful indirect evidence. Scientists believed they existed for strong reasons. Yet many people still wondered something simple. Have we actually seen one? The question sounds straightforward, but black holes complicate the meaning of seeing. By definition, a black hole does not emit light from within its event horizon. There is no ordinary photograph of the black hole itself. What can be observed are effects: the motion of nearby stars, radiation from infalling matter, the bending of light, ripples in space-time from mergers. In that sense, black holes are seen through consequences. This may sound indirect, but much of science works this way. Electrons are not observed like pebbles on a table, yet their effects are unmistakable. Black holes belong to that tradition. One early line of evidence came from binary systems. A visible star orbiting an unseen companion. By studying the orbit, astronomers could estimate the hidden object's mass. If the mass exceeded the known limits for neutron stars, a black hole became the leading explanation. One famous example is Cygnus X1. Discovered as a strong X-ray source, it became one of the earliest compelling black hole candidates. The X-rays mattered because matter falling toward a compact object can heat enormously in an accretion disk. Hot gas glows in high-energy radiation. The black hole remains dark, but the surrounding process shines. This became a pattern. Black holes revealed themselves through their environments. Yet perhaps the most elegant evidence came not from glowing gas, but from stars moving around invisible mass. At the center of the Milky Way, astronomers spent decades tracking individual stars near Sagittarius A. One star, often called S2, follows a tight, elongated orbit. Its motion implied a compact object of about 4 million solar masses, packed into a remarkably small region. Alternatives became exceedingly difficult to sustain. A supermassive black hole fit the evidence. There is something quiet and beautiful in that method. Watching stars move, letting gravity reveal the unseen. No dramatic cosmic photograph was needed. The evidence emerged from patient observation. And yet, eventually, something even closer to a picture arrived. In 2019, the Event Horizon Telescope collaboration released the first image associated with a black hole. Specifically, the shadow of the supermassive black hole in Messier 87. Many remember the glowing orange ring. It quickly became iconic. But what exactly was shown? Not the event horizon directly, and not the black hole as a visible object. Rather, the image captured emission from hot plasma around the black hole, shaped by gravity and light bending. At the center appeared a dark shadow. That shadow corresponds roughly to photons being captured or strongly redirected by the black hole's gravity. In a sense, it was a silhouette cast by spacetime. A remarkable phrase. and remarkably accurate. The technical achievement was extraordinary. No single telescope could resolve something so small at such distance. So astronomers linked radio observatories around Earth using very long baseline interferometry, effectively creating a planet-sized observing system. Data were gathered, correlated, reconstructed. Years of work produced that quiet, glowing ring. It was not only an image, it was a triumph of method. And importantly, the observed shadow size agreed with predictions from general relativity. Theory and observation met beautifully. Later, the collaboration released an image associated with Sagittarius A times as well. More difficult in some ways because the system varies rapidly. Yet again, a hidden gravitational structure became partly visible through surrounding light. Still, sight is only one way black holes became observable. Another came through sound. Or rather, through signals often translated into sound. In 2015, the LIGO scientific collaboration detected gravitational waves from merging black holes. This was historic. Einstein had predicted gravitational waves a century earlier, ripples in space-time produced by accelerating masses. But now they were measured directly. Two black holes spiraled inward, merged, released energy in gravitational waves. For a brief moment, the power radiated in those waves exceeded the light output of all stars in the observable universe combined. Yet by the time the signal reached Earth, it was astonishingly tiny. A minuscule stretching and squeezing of space-time itself. LIGO detected distortions smaller than a proton's width over kilometers. A precision almost hard to comprehend. When scientists convert the signal to audible frequencies, one hears a rising chirp, a brief upward sweep. People sometimes call it hearing black holes collide. Poetic, though technically it is hearing translated gravitational wave data. Still, something profound happened. We did not merely infer black holes from nearby effects. We observed them merging through space-time ripples. A new form of astronomy was born. Since then, many black hole merger events have been detected. Each one extends confidence. Each one probes strong gravity. And again, general relativity has passed remarkable tests. It is worth pausing on how many layers of observation now converge. Stellar orbits, X-ray binaries, black hole shadows, gravitational waves. Different methods, different instruments, different phenomena. Yet a coherent picture emerges. That convergence is powerful. Science often becomes persuasive, not through one dramatic proof, but through many independent lines meeting. There is also something philosophically interesting here. Human senses alone could never perceive black holes directly. Yet by extending perception through instruments and mathematics, we reach them. Telescopes lengthened sight. Interferometers sensed distortions in space-time. Equations guided interpretation. Observation became broader than ordinary seeing. This matters because people sometimes imagine science advances only by looking harder. Often, it advances by learning entirely new ways to look. Black holes are a beautiful example. There is another subtle point. The famous black hole image did not end mystery. It deepened it. It raised questions about magnetic fields, plasma behavior, accretion dynamics, spin. Every answer opened more questions. Good science often works that way. Even gravitational waves opened new puzzles. How common are certain merger masses? How do binary black holes form? What might future detectors reveal about supermassive mergers? The story is still unfolding. There is also future promise. Planned observatories, such as Laser Interferometer Space Antenna, aim to detect lower-frequency gravitational waves from enormous systems. Space-based interferometry may widen the listening range of astronomy. The quiet universe may speak in more frequencies yet. And the Event Horizon Telescope itself continues improving. Higher resolution may reveal changing structures near horizons. Observation inches closer, though always indirectly, toward regions once thought forever beyond empirical reach. That arc is extraordinary. From Michel imagining dark stars in the 18th century, to equations, to inference, to images and gravitational waves. The impossible became observable. Yet perhaps the most beautiful thing is how humble the observations often are. Tiny orbital shifts, faint radio signals, minuscule distortions. Great mysteries revealed through delicate measurements. There is calm in that. The universe need not shout to be understood. And once black holes became observable, another question naturally sharpened. If these objects are real, and if their horizons are meaningful physical boundaries, what happens over immense spans of time? Are black holes eternal? Or can even darkness fade? For many years, people assumed black holes only grow. Matter falls in. Mass increases. But quantum theory suggested a stranger possibility. Black holes might slowly radiate. They might evaporate. This idea changed everything, because it connected black holes not only to gravity, but to quantum physics and thermodynamics. And with it came one of the deepest puzzles in modern science. If black holes can fade away, what becomes of what fell into them? That question waits ahead. So now we can move gently toward Hawking radiation and the possibility that even black holes may not be eternal. For a long time, black holes were imagined as ultimate absorbers. Things could fall in. Nothing could come out. That seemed almost definitional. A black hole was black because it emitted nothing. And then, in the 1970s, something astonishing happened. That certainty began to soften. Stephen Hawking showed that when quantum theory is considered near an event horizon, black holes may not be entirely black. They may radiate, very faintly, very slowly, but genuinely radiate. This idea is called Hawking radiation. It changed black hole physics profoundly. Because if black holes radiate energy, they can lose mass. And if they lose mass, they may eventually evaporate. Even darkness, it seemed, might not be eternal. To appreciate why this was so surprising, it helps to move carefully. Black holes emerge from general relativity. Hawking radiation emerges from combining relativity with quantum field theory in curved spacetime. Wikipedia 1. It sits at a boundary between theories, and boundaries often reveal surprises. Popular explanations often describe pairs of virtual particles appearing near the horizon, with one escaping and one falling inward. This picture can be helpful as an intuition, but it is simplified. The deeper derivation is subtler. It arises because quantum fields behave differently in curved spacetime, and what counts as empty vacuum for one observer may not appear empty for another. In that sense, radiation emerges from the structure of quantum fields near the horizon, not literally from tiny particles being sliced in half at the boundary. That distinction matters. It keeps the mystery accurate. Still, the simplified picture carries a useful image. Something about the horizon allows energy to be associated with outgoing radiation, and a black hole pays a price. It loses mass. This was revolutionary, because previously black holes seemed only to grow. Matter falls in. Mass increases. Hawking added a slow reverse process. A black hole can leak energy back into the universe. The radiation is extraordinarily weak for astrophysical black holes. A stellar black hole has a temperature far colder than the cosmic microwave background. So in today's universe, such black holes absorb more than they emit. They grow rather than evaporate. For now, but over unimaginable timescales, in a far colder future universe, evaporation could dominate. And here another remarkable idea enters. Black holes have temperature. That sentence would have sounded almost absurd before the 1970s. Temperature suggests thermodynamics, heat, entropy. Yet black holes seem to participate in all of these. This was linked to earlier work by Jacob Bekenstein, who proposed black holes should possess entropy related to the area of their event horizons. Not their volume, their area. That was strange already. Hawking's result gave it deeper support. The horizon became not merely a geometric boundary, but a thermodynamic one. This was a profound shift. Gravity and thermodynamics began whispering to one another. Sometimes people say black holes glow. In a sense, yes, but unimaginably faintly for large ones. And something counterintuitive happens. Smaller black holes are hotter. Larger black holes are colder. That reverses ordinary intuition. Usually, bigger objects hold more heat. But black hole temperature falls as mass rises. Science focus too. And because smaller black holes radiate more strongly, evaporation accelerates as mass decreases. A long, slow fading may end in a rapid final phase, at least in the semi-classical picture. There are open questions near the very end. Quantum gravity may matter there. But even without resolving those, the conceptual shift was enormous. Black holes were no longer perfectly black, no longer eternal by default. And this naturally led physicists toward an even deeper puzzle: information. In everyday language, information can sound abstract. but in physics, it refers, roughly speaking, to the detailed state of a system. The arrangement of particles, their quantum properties, the distinctions that make one state different from another. Quantum mechanics strongly suggests this information is not simply destroyed. But Hawking's original calculation seemed to imply the radiation is thermal, featureless in a crucial sense, dependent mainly on the black hole's bulk properties, not the detailed history of what fell in. Wikipedia 1. And here the paradox appeared. Suppose matter carrying rich quantum information falls into a black hole. Suppose the black hole eventually evaporates entirely into thermal radiation. Where did the information go? Was it destroyed? If so, quantum theory faces trouble. If not, something in our picture is incomplete. This became the black hole information paradox. It is difficult to overstate how important this became, because it is not merely a puzzle about black holes. It touches the consistency of fundamental physics. General relativity, quantum mechanics, thermodynamics, all seem to meet here, and not quite peacefully. There is something beautiful in how calm the puzzle sounds. If black holes evaporate, what happens to information? Simple words, profound consequences. Many ideas have been proposed. Perhaps information is subtly encoded in correlations within Hawking radiation. Perhaps horizons have richer structure than once thought. Perhaps holographic descriptions hold the key. Some recent work involving the page curve and quantum gravity calculations has strengthened hope that information may ultimately be preserved. Wikipedia 1. But a full, universally agreed final resolution remains elusive. That uncertainty is part of the mystery. There is also poetry in the timescales involved. A solar mass black hole would take vastly longer than the current age of the universe to evaporate. Inconceivably longer. We are discussing processes on almost absurd durations. Trillion upon trillion ages. And yet, physics follows them seriously. Thought reaches where observation cannot yet go. Sometimes people ask whether Hawking radiation has been directly observed from astrophysical black holes. Not directly. It is far too weak to detect from known black holes. But analog systems have shown Hawking-like effects in laboratory settings, offering partial support for the broader framework. Nature 3. Again, theory leads where measurement is still delicate. There is a recurring theme in black hole physics. What first sounds impossible often becomes coherent. Black holes can form. Horizons can exist. Time can stretch. And now even black holes can radiate. Each step widens reality a little. Hawking radiation also hints that space-time may have hidden microscopic structure, because thermodynamics usually reflects underlying degrees of freedom. Molecules explain gas entropy. What explains black hole entropy? That question reaches toward quantum gravity. Some suspect black holes are clues to the deeper fabric of space-time itself. And perhaps that is why this topic feels so compelling. A dark object, once imagined as an endpoint, becomes a doorway into deeper laws. Even evaporation becomes philosophical. If the most absorbing structures in the universe slowly dissolve, permanence itself feels different. Yet none of this is mystical. It is the quiet strangeness of theory following its logic. Hawking once overturned the thought that black holes only hide things. They may also reveal something fundamental. And still, we have only arrived at the threshold of the paradox. Because once one asks whether information survives evaporation, deeper ideas begin pressing forward. What does it mean for information to be stored on a horizon? Could reality itself be described holographically? Could space-time emerge from information? These questions grew partly from trying to resolve what Hawking uncovered: a quiet radiation leading toward radical ideas. There is something fitting in that. From faint thermal leakage comes one of the boldest conceptual revolutions in modern physics. But before holography, the paradox itself deserves to stand in the mind for a moment. Matter falls in. Black holes radiate. Information should not be destroyed. These statements pull against one another. Somewhere in their tension lies deeper understanding. So now we can move gently toward the information paradox itself, and why black holes may force us to rethink what reality is made of. The information paradox begins with a tension. Not a contradiction we fully understand, but a tension between deep principles. Quantum mechanics suggests information is preserved. General relativity permits black holes with horizons. Hawking radiation suggests black holes may evaporate. Hold those three ideas together, and something strains. That strain became one of modern physics' great puzzles. To approach it calmly, it helps to ask what physicists mean by information. It is not everyday information, like a fact written in a notebook. It means the full, detailed specification of a physical state. Which particles exist, their quantum numbers, their correlations, the distinctions that make one arrangement different from another. In ordinary quantum theory, evolution is expected to preserve that information. It may disperse. It may become practically unrecoverable, but not fundamentally destroyed. That principle is closely related to unitarity. Unitarity. A quiet technical word with enormous consequence. Now imagine a star collapses into a black hole, or a complex object falls in. From outside, a black hole in classical general relativity can often be characterized by only a few quantities: mass, charge, angular momentum. This led to the phrase, black holes have no hair. A metaphor meaning many details seem hidden from outside description. Already there is mystery. What became of all the rich detail of what fell in? Then Hawking radiation sharpened the puzzle. If the emitted radiation is purely thermal in the original semi-classical picture, it seems not to carry those detailed distinctions out again. And if the black hole evaporates entirely, where is the information? Lost. Hidden forever. Somehow encoded. These possibilities do not sit equally comfortably with known physics. This is the paradox. It sounds almost innocent when stated plainly. If black holes disappear, what happens to what fell into them? Yet behind that question stand foundational principles. Some early reactions entertained the possibility information really might be destroyed, but many physicists resisted that conclusion strongly. It seemed too disruptive to quantum theory. So alternatives were sought. One possibility is that Hawking radiation is not exactly featureless after all. Perhaps subtle correlations encode information in ways the original approximation missed. That has become a central direction. There is a useful thought experiment often discussed. Imagine throwing an encyclopedia into a black hole. The atoms disappear beyond the horizon. Later, the black hole evaporates. Does the information once contained in the encyclopedia survive somehow in the outgoing radiation? Perhaps scrambled beyond practical recovery, yet preserved in principle. Many now lean toward some form of yes. But how remains subtle. This led to studies of black hole entropy and information flow over time. One famous idea is the page curve. Very roughly, it describes how the entropy of radiation might evolve if information is ultimately preserved. For years, it served as a guidepost. More recently, calculations involving quantum extremal surfaces and replica wormholes gave striking support to recovering page curve-like behavior in certain models. Many saw this as important progress, not universal closure, but a real deepening. It suggested semi-classical gravity may contain richer structure than once thought. There were also more dramatic proposals. One famous controversy involved firewalls. Firewall paradox. The concern arose because preserving quantum information, maintaining ordinary horizon smoothness, and respecting certain entanglement assumptions seemed difficult to satisfy simultaneously. Some argued the horizon might become violently energetic, a firewall breaking the expectation of gentle crossing. This was controversial and remains debated. Its importance lay partly in exposing tensions clearly. Sometimes paradoxes sharpen understanding even without final answers. Another beautiful thread is black hole complementarity. Black hole complementarity. Roughly, it explored whether outside and infalling descriptions might both remain valid without contradiction, though not simultaneously accessible in naive ways. Again, subtle. Again, motivated by preserving consistency. There is something almost philosophical in how black holes force questions about what counts as a complete description. Yet this is still physics. Technical, rigorous, mathematical. It only brushes philosophy because the stakes are foundational. There is also a gentler way to feel the paradox. Physics usually likes reversibility at deep levels. Given complete information, the laws can, in principle, evolve states consistently. Black holes seem to threaten a one-way forgetting. That felt alien to quantum structure. Hence the discomfort. And discomfort in science can be fruitful. It marks where assumptions meet resistance. Some modern thinking increasingly treats information as central, not peripheral. Not merely bookkeeping, but structural. Black holes helped encourage that shift. There is another subtle distinction worth keeping. Information being preserved in principle does not mean recoverable in practice. Those are different claims. A scrambled egg may preserve microscopic information under fundamental laws, yet be practically impossible to reconstruct. Black hole information may be analogous in spirit. Preservation need not mean accessibility. This helps soften misconceptions. Sometimes popular treatments say black holes destroy information as if established fact. Better to say the possibility raised a paradox, and much work suggests deeper preservation may hold. Precision matters. There is also beauty in how multiple disciplines converge here. Quantum field theory, gravity, thermodynamics, information theory. Black holes became crossroads. That perhaps explains their unusual grip on imagination. They are not only astronomical objects, they are testing grounds for fundamentals. Even the phrase information paradox has a quiet elegance. It sounds almost abstract, yet hidden inside is a question about whether the universe forgets. That feels almost intimate. And perhaps the deeper surprise is that attempts to answer this puzzle led toward still more radical ideas. Entropy on horizons, holographic descriptions, space-time emerging from quantum relationships. The paradox did not merely threaten theory, it generated new theory. That is often how physics grows. A puzzle first appears destructive. Later it proves generative. One can even say black holes transformed from endpoints into laboratories. There is something quietly reassuring in that. Mystery need not mean failure. It can be an engine of deeper structure. Of course, open questions remain. No final universal consensus wraps every detail. That honesty matters. The frontier is still alive. Yet broad confidence has grown that black holes probably do not overthrow quantum consistency. Rather, they push us toward richer formulations. And that naturally leads onward. Because once information seems central, a startling thought emerges. Could spacetime itself somehow be tied to information? Could geometry be less fundamental than we assumed? These questions open into the holographic principle, one of the boldest conceptual developments black holes helped inspire. So now we can move gently toward holography, and the possibility that reality may be encoded in ways stranger than space alone suggests. Sometimes, the deepest scientific ideas begin as attempts to solve narrower problems. A puzzle appears. A contradiction seems to form. And in resolving it, an unexpected new view of reality emerges. The holographic principle is one of those ideas. It did not begin as philosophy. It grew partly from trying to understand black holes. And though the name can sound mystical, the idea is precise in origin. It belongs to theoretical physics. To approach it calmly, it helps to begin with something familiar. A hologram stores three-dimensional information on a two-dimensional surface. A flat pattern can encode a richer-seeming depth. That simple image inspired the metaphor. The physics idea is subtler. It suggests that, in some contexts, information describing a volume of space may be representable on a lower dimensional boundary. In rough language, a three-dimensional region might be fully described by information on a two-dimensional surface. Why would anyone suspect such a strange thing? Black holes helped inspire it. Recall black hole entropy. Bekenstein and Hawking found something remarkable. A black hole's entropy appears proportional to the area of its event horizon, not its volume. That was deeply unexpected. Many physical systems scale with volume. More space, more room for degrees of freedom. But black holes seem to hint that information content might scale with area. That whisper became provocative. Perhaps this was not peculiar only to black holes. Perhaps it reflected something deeper about space-time itself. In the 1990s, thinkers, including Gerard Hooft and Leonard Susskind, pushed this intuition into what became called the holographic principle. At first, it sounded almost too radical. Yet it emerged from concrete attempts to preserve consistency in gravity and quantum theory. Then came a major development. Juan Maldacena proposed what is often called ADS CFT correspondence. ADS CFT correspondence. The name can sound forbidding, but its core claim is elegant. In certain mathematical settings, a gravitational theory in a higher dimensional space can be equivalent to a quantum field theory without gravity living on its boundary. Two very different descriptions, yet mathematically dual. One can translate between them. This was astonishing because it made holography more than speculation. It became a concrete framework. Now, an important caution. Our universe is not exactly the simple anti-de Sitter geometry used in the classic correspondence. So one must be careful not to overstate. Physicists do not claim ordinary reality has been proven literally to be a hologram in a science fiction sense. But the principle has become profoundly influential. It suggests surprising ways gravity and quantum information may connect. And black holes sit near the heart of that connection. Sometimes people phrase it dramatically. The universe might be a hologram. That phrase can mislead. It can sound like ordinary reality is fake or projected. That is not the claim. The idea concerns equivalent descriptions of physical information, not an illusion replacing reality. Precision matters. There is another reason holography became compelling. It offered possible tools for the black hole information paradox. If information can be encoded at boundaries, perhaps event horizons preserve information in subtle ways. Perhaps what seemed lost is not lost at all. This remains part of an active story. But the conceptual shift was immense. Black holes went from threatening the foundations of quantum theory to perhaps illuminating them. There is a beautiful irony there. The darkest objects becoming sources of conceptual light. Holography has also influenced thinking beyond black holes. It has been used in studies of quantum matter, strongly coupled systems, and even aspects of condensed matter theory. This cross-pollination is part of its power. A deep idea migrates. But perhaps the most dreamlike implication came from another possibility. Maybe space-time itself is emergent. That word deserves gentleness. Emergent. It means not fundamental in the simplest sense, but arising from deeper ingredients. Temperature is emergent from molecular motion. A wave can emerge from many water molecules moving. Could space itself emerge from something deeper? Some modern work explores whether space-time geometry may be related to patterns of quantum entanglement. Quantum entanglement. This is still developing and often speculative, but it has become a serious area of thought. The suggestion is astonishingly quiet. Perhaps geometry arises from relationships among quantum information. If so, black holes may be clues to how space-time is woven. This does not mean the floor beneath you is unreal, or that space is somehow fake. Emergence does not imply unreality. It implies layered explanation. Water is real, though fluidity emerges from molecules. Likewise, space-time could be real and emergent. These distinctions matter. Sometimes a single sentence captures the quiet radicalness. Black holes may have led physicists to suspect information could be more fundamental than geometry. That is a profound inversion. We usually think space comes first. Information describes what is in space. Holographic thinking sometimes hints the relationship may run deeper. Even entropy acquires new depth here. Once it seemed a thermodynamic bookkeeping quantity. With black holes, it began sounding like a clue about microscopic structure. Clues often arrive quietly in physics. A coefficient in an equation, a scaling law, a paradox. Entire revolutions can grow from them. It is also worth noting what holography does not yet do. It does not provide a finished theory of quantum gravity. It does not resolve every black hole mystery. It is a powerful framework, not a completed final answer. Scientific humility belongs here. Yet even as framework, it changed the conversation. Few ideas have so deeply influenced modern theoretical physics. There is a meditative quality in how this emerged. We began with collapsing stars, then horizons, then evaporation, then information. And now, quietly, perhaps the fabric of space itself comes into question. The journey widened without ever abandoning logic. Some researchers even explore links between wormholes and entanglement, often summarized by the phrase ER equals EPR, ER equals EPR conjecture. This remains speculative. But again, black holes sit nearby in the conceptual terrain. It is striking how often black holes lead thought toward unexpected unity. Gravity meeting information, geometry meeting thermodynamics, horizons meeting quantum entanglement. Separate domains begin to speak to one another. And still, one can keep the emotional tone simple. None of this requires imagining reality as illusion. None requires abandoning common sense in ordinary life. It simply suggests our deepest physical descriptions may be richer than surface appearances. Perhaps that is enough wonder. There is also something historically moving about it. Einstein likely did not foresee black holes inspiring holography. Michel certainly did not. Ideas can travel farther than their originators imagine. A problem about trapped light can echo into questions about the architecture of reality. That is one of science's quiet beauties. Yet despite all these grand ideas, much remains unresolved. Do singularities truly exist physically? What exactly resolves them in quantum gravity? Are black hole interiors as classical theory suggests? Does holography fully illuminate those questions, or only part of them? These uncertainties matter. Mystery remains honest when uncertainty remains visible. And perhaps that leads naturally onward. For after surveying these bold conceptual possibilities, one may ask more plainly, what mysteries are still open? Which questions remain unsettled even now? Where do our theories strain? Black holes still hold many unsolved problems, some technical, some foundational. And after wandering through horizons, evaporation, and holography, it feels fitting to gather those mysteries into view. So now we can move gently toward the unsolved questions at the edge of black hole physics. Even after a century of theory and decades of growing observation, black holes remain unfinished questions. We have learned much, yet much remains unsettled. This is not a weakness of science. It is often how mature science looks at the frontier. A mixture of confidence and incompleteness. Some mysteries concern observation. Some concern theory. Some lie where those meet. It is fitting to gather them quietly. Perhaps the oldest unresolved question sits at the center. What truly happens at singularities? In classical general relativity, singularities appear as places where known description breaks down. Infinite curvature, infinite density in the formal picture. Many physicists suspect literal infinities signal not physical reality, but limits of the theory. Something deeper may replace the classical singularity. But what? A complete theory of quantum gravity remains absent. That absence sits behind many mysteries. Several approaches seek answers. String theory offers one broad framework. Loop quantum gravity offers another. There are others too, none yet universally accepted as final. So the interior fate of collapse remains open. Another mystery concerns event horizons themselves. Are they exactly as classical relativity describes in nature under all conditions? Most evidence supports horizons strongly. Yet subtle alternatives have occasionally been proposed. Exotic, compact objects, gravastars, other speculative possibilities. None has displaced black holes, but exploring alternatives helps test assumptions. Good science often does that. Then there is the information paradox, still not fully closed despite profound progress. How exactly information emerges, how interior and exterior descriptions reconcile, whether current proposed resolutions are complete. These remain active questions. The frontier is moving, not finished. Another unresolved domain concerns black hole formation in the early universe. Could primordial black holes have formed soon after the Big Bang? Primordial black hole. If so, could some contribute to dark matter? This remains uncertain and much studied. It links black holes to one of cosmology's biggest puzzles. There are mysteries of growth, too. Supermassive black holes appeared surprisingly early in cosmic history. How did some grow so massive so fast? Were seeds unusually large? Was accretion extraordinarily efficient? Did repeated mergers dominate? Observations continue refining the story. Sometimes, mystery lies not in strange new physics, but in astrophysical history still being reconstructed. Black hole spin is another frontier. Rotating black holes can store enormous rotational energy. Measuring spins precisely and understanding their histories can illuminate how black holes grew and interacted with galaxies. Even something as seemingly simple as how fast are they spinning opens rich questions. There are mysteries tied to observation itself. We have imaged shadows of supermassive black holes through the Event Horizon Telescope. Extraordinary. Yet, resolution remains limited. Future instruments may reveal time-variable structures in greater detail, perhaps testing relativity in stronger regimes. Observation may yet surprise theory. And then there are gravitational waves. LIGO opened a new window by hearing black hole mergers. Already they have revealed unexpected populations, including black holes with masses that challenged simple expectations. More detections may reshape formation theories further. Listening has become part of black hole astronomy. That still feels remarkable. Some mysteries are almost conceptual riddles. Does space-time emerge from quantum entanglement in some deep sense? If so, black holes may be clues to space-time's architecture itself. But how literal is that picture? Here, speculation and serious theory sometimes sit close together. Care is needed. Another open question concerns cosmic censorship. Cosmic censorship hypothesis. Very roughly, it concerns whether singularities are always hidden behind horizons rather than exposed nakedly to outside observers. It sounds almost poetic, but it is technical and profound. Is nature protecting predictability in this way? The question is not fully resolved in all forms. Even old questions can remain alive. There is also the matter of Hawking radiation itself. It is one of the most celebrated theoretical predictions in modern physics. Yet direct observational confirmation from astrophysical black holes remains beyond present reach. The effect is too faint for large black holes. So a central pillar of black hole theory still awaits direct empirical confirmation. That is worth remembering. Science often contains such asymmetries. Strong theory ahead of direct measurement. Another mystery lies in intermediate mass black holes. Intermediate mass black hole. Stellar black holes and supermassive ones are well established, but the population in between has long been harder to map. Are they common stepping stones in growth, or rarer than expected? Ongoing evidence continues to sharpen the picture. There is a gentle lesson in all these examples. Black hole mysteries are not one mystery. They are many layered mysteries. Some may resolve through better telescopes, some through deeper mathematics, some through entirely new theory, perhaps most through combinations. And it is possible some cherished intuitions will have to change again. Black holes have repeatedly forced revision. First, impossible curiosities. Then, accepted solutions. Then, thermodynamic objects. Then, information puzzles. Why assume surprises are over? There is even mystery in the emotional pull black holes exert. Why do they fascinate so deeply? Perhaps because they gather extremes. Gravity at its strongest. Time behaving strangely. Visibility failing. Theory straining. They sit where boundaries appear. Human thought is often drawn there. Yet perhaps the most honest, unresolved question is simple. What are we still not even asking correctly? At True Frontiers, the deepest missing piece may be a question not yet formulated. Science history repeatedly shows this. Before relativity, who asked whether gravity was geometry? Before quantum mechanics, who framed uncertainty as principle? Perhaps black holes await similar conceptual shifts. That possibility keeps the subject alive, not merely as solved textbook material, but as living inquiry. And after gathering open mysteries, a final widening remains. Black holes do not only challenge present theory, they may also shape the distant future of the universe itself. For if Hawking evaporation holds and cosmic expansion continues, black holes may be among the longest-lived structures in existence. Their mystery stretches not only inward toward singularity, but forward toward the end of cosmic time. So now we can move gently toward the far future and the strange possibility that black holes may outlive almost everything else in the universe. Black holes are often spoken of as endpoints, final remnants of collapse, cosmic graves of stars. But in another sense, they may be long-lived participants in the universe's far future. To think about that future, we have to leave familiar timescales behind. Not millions of years, not billions. Much farther. Cosmology sometimes invites a different kind of imagination. Quiet, patient, almost geological in spirit. We begin with what we know now. The universe contains stars still burning, galaxies still forming stars in some regions. But stars do not shine forever. Their fuel is finite. Over immense spans, ordinary star formation is expected to decline. Existing stars age and die. New ones become rarer. This era is sometimes called the stelliferous era, the age of stars. We live within it now. Yet beyond it lies a quieter future, a universe of remnants. White dwarfs, neutron stars, black holes. Over truly vast durations, even galaxies may change profoundly through gravitational encounters. Stars may be ejected, orbits reshaped. Some matter may drift into central black holes. If protons are ultimately unstable, as some speculative grand unified theories allow, though not confirmed experimentally, ordinary matter could decay over fantastically long times. If proton decay does not occur, some details differ. The distant future depends partly on unknown physics. But in many scenarios, black holes become among the longest-lasting structures. There is something almost paradoxical in that. Objects born from stellar death may outlast stars themselves. And if Hawking radiation is correct, even they are not eternal, only extraordinarily persistent. Consider a stellar black hole. Its evaporation time is so vast, it dwarfs the current age of the universe beyond ordinary comprehension. Supermassive black holes last longer still, inconceivably longer. For ages upon ages, they may remain after starlight fades. Some cosmological narratives call this the black hole era, a distant epoch when black holes dominate what complex structures remain. The phrase has a quiet grandeur, the black hole era. Yet even then, Hawking radiation whispers its slow work. Mass leaks away, imperceptibly at first. A slow surrender of darkness back into faint radiation. It is difficult to speak of such durations without slipping into abstraction. So sometimes it helps simply to note the scale. Trillion upon trillion upon trillion years, and vastly beyond. Numbers become almost ceremonial at that point. They point rather than fully convey. In the semi-classical picture, a black hole eventually evaporates completely, perhaps ending in a final energetic phase, though the ultimate end may depend on quantum gravity. There are open questions. Does evaporation truly go to completion? Could remnants remain? Some possibilities are still debated. Mystery persists even at the end of endings. Yet the broad image remains powerful. Even black holes may fade. There is a certain stillness in that thought. The darkest objects in nature slowly dissolving into thin radiation in a cold, expanding cosmos. And what then? Some cosmological scenarios suggest a universe drifting toward heat death of the universe. Maximum entropy. No large free energy gradients to sustain complex processes as we know them. A very quiet cosmos indeed. It is worth being careful. These are extrapolations grounded in known physics, but they involve assumptions. Cosmology at such scales is not observationally direct in the ordinary sense. It is reasoned projection, beautifully disciplined, but still projection. That humility matters. There are alternative, speculative endings too. If dark energy behaves differently than currently thought, possibilities shift. Some once discussed scenarios imagined a big rip, though present evidence does not require it. Others involve cyclic ideas, though these remain uncertain. But within standard cosmological expectations, black hole evaporation sits as one of the quiet closing acts. There is another profound thread here. Black holes began in our story as mysterious absorbers, places where things vanish from view. Yet in the far future story, they become clocks, markers of unimaginably slow change. They measure cosmic patience. And because black holes touch the information paradox, their ultimate fate may also touch whether information survives forever in some encoded way. Even the end of black holes may carry unresolved foundational significance. The far future remains linked to deep theory. There is something almost meditative about how the scale keeps expanding. We began this journey with ancient stargazers looking upward, then dark stars, then horizons, then quantum paradoxes. Now we sit in eras beyond stars themselves. The mystery widened without losing continuity. Some physicists have reflected that black holes may be among the last monuments of complexity before a simpler cosmic state. That may sound poetic, yet it arises naturally from certain extrapolations. Long after suns are gone, their collapsed descendants may linger. It invites a different sense of time. Human history becomes a brief flicker. Civilizations, a smaller flicker still. And yet minds within that flicker can contemplate the black hole era. There is quiet wonder in that. Sometimes people hear these distant futures and feel bleakness. But there is another way to hear them, as testimony to the depth of lawful structure in the universe. Physics can meaningfully trace consequences across almost inconceivable spans. That is extraordinary. And even within the far future silence, uncertainty leaves openness. We do not yet possess a full theory of quantum gravity. Surprises may await. Perhaps the final chapters differ from our present extrapolations. Black holes have repeatedly surprised physics. It would be fitting if they still hold further surprises at the end. There is also a beautiful inversion to notice. Early in the story, black holes seemed like endings. In the cosmic future, they become among the longest stories. They persist where much else fades. And eventually, if Hawking was right, even those long stories end not with explosion and drama, but with gradual evaporation. A soft fading. That feels strangely aligned with the quiet spirit of this journey. It may also return us to a philosophical softness. Black holes once seemed symbols of ultimate concealment. Yet they became laboratories for understanding gravity, information, thermodynamics, and perhaps space-time itself. Even in imagining their disappearance, they continue teaching. Perhaps mysteries do that. They deepen rather than simply resolve. If one listens gently, a pattern has repeated throughout. Invisible stars imagined. Gravity reinterpreted. Collapsing suns. Event horizons. Quantum radiation. Holographic hints. Cosmic endings. At each stage, black holes were less objects than meeting points. Places where theories touch. Places where intuition thins. Perhaps that is the true mystery of black holes. Not simply what lies inside them, but why they sit so persistently at the edges of understanding. And maybe that is a fitting place to rest. Not with final answers, but with a quieter sense of scale. A universe where stars are born and die, where gravity can fold space into horizons, where even darkness may slowly evaporate, and where, across unimaginable ages, the laws of nature continue their patient unfolding. In that long unfolding, black holes are not interruptions of order. They are part of it, strange, profound, and lawful. And as the far future grows quiet in thought, perhaps the mystery itself grows quiet too. Not solved, but softened. A final dark horizon, slowly dissolving into silence.